We have to understand why every incipient perturbation disturbance that grows into a tropical storm doesn't grow into a category 5 storm, a major hurricane or a super typhoon. Obviously there are environmental factors that govern the intensity. We looked at basic processes of Sisk and Vichy and so on that can lead to potential intensity growing. Look at this intensity against SST for the North Atlantic and Western North Pacific, Australian and North Indian, South Indian basins. These are for storms over a 20-year period, 1967 to 1986. You can see that where there is good data, there is more of a systematic relation, good observations from recons or satellites or whatever. So you can see that in the North Atlantic and Western North Pacific, this orange line here corresponds to 29-degree SST threshold, and there is a systematic increase in the intensity in terms of meter per second maximum sustained winds in these both places, whereas the relation is not as clear in the regions where there haven't been that many observations of Australia, North India and South India. But nonetheless, if you then look at this figure, and you can still draw some conclusions. Basins without regular recon flights, panels C to E, so C, D and E, have intensity distributions that emphasize key intensity values, likely reflecting a dependence on satellite-based algorithms to estimate intensity. So we will see intensity estimations in the next chapter, and there is quite a bit of subjectivity there, and multiple data streams are needed to estimate the intensity, so that could be one issue. Storm intensity increases dramatically for tropical ST greater than 25 degree or so. So you can see that once you cross 25, there is generally a significant increase in intensity compared to SSTs colder than that. That works even here. The two basins with reconnaissance show a uniform distribution of intensity across the observed SST range applicable. This means that stronger storms are restricted to a smaller, warmer range of SSTs. So stronger storms are in this band, which are closer to much more restricted than these bands at cooler temperatures. We can kind of combine that with frequency of cyclone occurrence versus intensity stratified by SST. So look at 27, 28, 29 and 30. Frequency of occurrence of storms of a particular intensity stratified by SST for the North Atlantic and Western North Pacific for 1 degree C SST bands. Since there are many fewer TC observations over 30 degrees C than 29 degrees centigrade, etc., frequencies are scaled so that maximum frequency for each SST is 100. So you take the disparities in observations and then adjust the scale so that maximum frequency is set to 100. This maximum frequency always coincides with the weakest intensity explored. So you can see weak intensities here end up producing maximum frequency of occurrence. Not surprising, because many of them don't grow to be major intense cyclones. This maximum frequency always coincides with the weakest intensity explored. All time periods for all storms occurring in the 20-year window are included. Okay, so maybe it's not very intuitive that the warmest SSTs of 29 and 30 here have obviously high frequencies of low intensity storms, but they drop off for higher intensity storms. There are multiple reasons. It happens in both in both the Western North Pacific and North Atlantic. There are of course differences in the details of the cyclogenesis processes, environmental conditions, SST distributions, islands along the way, and so on and so forth. But in general, warmest SSTs tend to occur near the equator, where rotation becomes planetary rotation becomes very small, which is not conducive for the incipient disturbance to grow. You need the rotation, obviously. Plus, by the time you are capturing the more intense cyclones, they have probably moved away from the warmest SSTs. Okay, so in both places you can see that the high frequencies are lower intensity storms. In both places, the 27-28 degree occurrences have these peaks below the lowest intensity, so that has to be explained as well. And here it has one peak, but here it has two peaks. Possibly a sampling issue, but nonetheless you can see that the occurrences are up and down as you go along. It's not monotonic, whereas here they are monotonic, increase towards lower intensities, or going the other way. As intensities increase, the frequencies drop. Here the highest frequencies are for higher intensity than the lower intensity, and then there are these kind of behaviors which you can look up as to why those happen. Okay. In terms of links between inner core dynamics, cyclone structure, and intensity, we already know that the Vichy mechanism, which has to bring moisture into the eye wall, has to come through the boundary layer, and as it is moving from higher pressures outside to lower pressures towards the eye, it has to remain moist and not expand and dry up, so condense and so on. So it has to pick up moisture along the way. There are sea sprays involved because at the surface you have strong winds, and of course heat fluxes, evaporation, and moistening of the boundary layer happens. So the core dynamics is related to the Vichy processes, and we have to worry about shear. That it is fairly clear now that many times a minimum level of shear favors re-intensification and translation of the cyclone, so that it doesn't get stuck and weaken by weakening by cooling the SSTs. Stability matters. The strong eye with lower pressures and stronger eye wall winds is going to have higher inertial stability, and this stability is weakens as we go up. So drier intrusions, Saharan air layer, all these sorts of things matter for the inner core dynamics, and inertial stability is not very immune to the fact that cool SSTs cut off the energy supply and then the cyclone can weaken. Okay, so weak vertical shear can intensify and creating the tilting on the down shear side, creating new convections and re-intensification, whereas very strong shear will obviously chop off the energy and not allow the outflow to be as cold, or the thermodynamics of the Carnot cycle to be as strong. The warm tropopause also can create the same issue of reducing the temperature difference, the thermodynamic energy available, and so on. So the inner core dynamics and cyclone structure and intensity are obviously all linked to each other. These are kind of general points. You can find papers which have looked at observed climatology of various levels of shear and the cyclone intensities and potential intensities, and they are not very well explained as to why some weak shears actually favor intensification, but the stronger shears chop it off. And it does matter to forecasts, obviously, because environmental conditions are important. Plus, Cyclone is not really an isolated entity. It is completely interacting with the environment, and it's affecting the wind shear and the steering winds as well. So all these things have to be kept in mind when we talk